Assalamu alaikum wa rahmatullah. Good morning. Welcome to my class of distributed and parallel computing. So today is only 1 hour. So we try to quickly go through concepts and terminologies of the parallel computing. So to find all videos, please go to my YouTube channel. Try to find all videos from there, and don't forget to subscribe and hit the bell to receive the updates about the newly uploaded videos on my channel to be up to date. Okay, guys, so what we need to take for today is the general and common concepts and terminologies. The class is going to be very quick because it's going to give a quick overview of the architecture, the common architecture, and the common concepts that we have to deal with through this course. Okay, so the first thing here, we are going to go through something called von Neumann architecture. Von Neumann architecture actually is for over 40 years, virtually all computers have followed a common machine model known as the von Neumann computer. So this architecture actually is very, very common. That's why most computers are following this architecture. And for this reason, we bring it here for your information, to understand about it, to read about it, in order to get really into the parallel computing and to understand how it works based on the basic architecture that's commonly used everywhere. So this architecture actually named after the Hungarian mathematician John von Neumann. Von Neumann computer uses the stored program concept. So this is one of the main concepts used through this architecture. The CPU executes a stored program that specifies a sequence of read and write operations on the memory. So based on this concept, actually, what they said about this architecture, that the program actually is going to be saved in the memory, and the program is only a group or a set of or a group of instructions that should deal with the data that's also saved in the memory. So the program and the data are saved into the memory. The program is all about a set of instructions that reads and write that data from or to the memory. Okay? This is a very basic concept about the von Neumann architecture. So just keep this in mind, because later we are going to go through the details in the coming classes. So you always need to keep this in mind. Okay? Okay, the basic design actually of that architecture is that the memory is used to store both program and data instructions. So both of the things, program and data, have to be saved into the memory. Okay, then the program instructions, when we say here program and data, so here we come to the program first. The program is a set of instructions that are coded data, which tell the computer to do something. So that program actually is about dealing or manipulating the data, certain data which is saved into the memory, to do something or some jobs. Okay, so here later we come to the data, which is the second part of this design. So the data is simply an information to be used by the program. So it's a necessary information that's needed by the program to complete that job. So again, into the memory, we have two things. Two parts have to be saved. The first part is program, the second part is data. Both parts actually are related or designed to do some job or to achieve some or certain job. So that program is a list or set of instructions that are designed to deal with that data to achieve that job. Okay? A central processing unit, which is called CPU, as you know, gets instructions and or data from memory. So the CPU should bring the program or the instructions of the program and also the data from the memory, right? So that CPU need also to decode the instructions and then sequentially perform them, because at any CPU in this world, any single CPU, only one instruction is going to be processed at a time. So at any point of time is only one instruction can be processed. Okay, so as we said, the program actually is a set of instructions that's saved into the memory, so the CPU will take them one by one, right? So the first instruction will come to the CPU, it will be executed. So if it needs some data, the data will be also called from the memory to achieve or to finish the first instruction. Then after that, we can go to the second, third, fourth, and so on. Okay, so it's a kind of serializing the execution of instructions inside the CPU. Okay, so both instructions and memory should be called by the CPU from the memory, and the instructions of the program must be executed one after another. Okay, so this is the main basic concept or the main basic design of the architecture. Okay, now we come to something called Flynn's classic taxonomy. Okay, so Flynn's classic taxonomy is very common also when it comes to parallel and parallel computing. So here in under this taxonomy, actually there are different ways to classify parallel computers. There are different ways to classify parallel computers. Okay, just keep this in mind. One of the more widely used classifications in use since 1966 until now is called Flynn's taxonomy. So this Flynn's taxonomy actually was placed or was introduced since the 1966, and it's still in use until this moment. Okay, until this moment. So it's more than or about 55 years, right? Yes, about 55 years. Okay. So Flynn's taxonomy distinguishes multiprocessor computer architectures according to how they can be classified along the two independent dimensions of instruction and data. So based on the previous design, as we mentioned here, we have two dimensions. The first dimension is the instructions or the program, and the second dimension is the data, right? So here, the Flynn's taxonomy actually is based on this two dimensions. Okay, so each of these dimensions can have only one of two possible status. So in every dimension, we have only two status, either single or multiple. So we will have single and single, single and multiple twice, and multiple with multiple. Okay, later we will see that in the coming slide. Okay, so as you can see here, this is the array of the taxonomy or the classification, which is called Flint's taxonomy. So here, as you can see, we have 2 dimensions array, right? So this 2 dimensions array has 2 columns and 2 rows. So these 2 columns actually are related to data, as you can see here, single data, multiple data. And these the second row actually is the first and second rows are about the single instruction and multiple instruction. So here you can see single instruction, and here is multiple instruction, So from here, we understand that we have only 2 dimensions. Okay, let me open the Paint and try to explain in more details for you how this can work. Okay, based on this, what do we have here actually is 2 dimensions. This is the first dimension, and here is the second dimension. Okay, so the first one here, let me draw arrows like that. Okay, so the first dimension here is all about data. Okay, the second one actually is all about instructions here, all about instructions. Okay, so as you can see here, this one actually is single. I will use S, and here this one is multiple, so I will use letter M. Okay, here is also single. This one is actually at this dimension, this one means single instruction, and this one means multiple instruction. And here on this dimension, this one means single data, and this one here means multiple data. Okay, so as you can see here, this cell actually is S and S, which means S or single instruction, single data. And this one actually is single instruction, multiple data. The other one here is multiple instruction, single data. And this one also finally is the multi-instruction, multi-data. Okay? What does this mean, guys? Okay, let us explain what does this could mean. Okay, let us keep this here. And let us draw some diagrams. So in this case, actually, of the first case here, which is called single instruction, single data. So in here, what do we have is 3 units. So this is the first unit, second unit, third unit. Okay, so the first one here is called control unit, and the other one here called processing unit. And then here we have memory that has data. Okay, so for data I'm going to use letter D. Okay, here in this case the control unit actually is going to control the processors and also the memory. So the data actually is going to be called from the memory here to the control unit. Then it will be given to the processing unit, and the processing unit could update that data or write other data or whatever. So the thing actually, the flow of the execution actually is going to be in this way. So the control unit actually is going to execute, or to allow the processing unit to execute only a single instruction per time. Okay, so at every point of time, only a single instruction is going to be processed based on only a single data. So if we have list of instructions, for example, we have list of instructions here. So that instruction list are from 1 to 100 instructions. So the CPU or the control unit actually is going to take them one by one. So it will execute the first instruction. It will select the first instruction, give it to the processing unit. The processing unit will execute it, will process it using that data. So maybe we can do like that, or it depends on what you want to explain. So the processing unit actually is going to execute that instruction using certain data, which is also single data at a time. Then after it finish, maybe the result could be passed to the second instruction, or maybe the second instruction is not related to the first one, so it can come here to the control unit, processed by the PU, and after that it could call, read or write some data, which is also single data, and so on until it finishes. So this is the what they call it, the structure of the first one, or how it works. Okay, the second one, or let us before that go here. We see this one actually is fully sequential. So this one is not related to any type of parallel. Okay, so this one is pure sequential processing architecture or design. Okay, the second one, we will go to the SIMD. So the SIMD actually, let me clean this. The SIMD actually is all about single control unit, multiprocessors, then one memory, or maybe shared memory. That memory should have what they call it, multiple data. Okay, so here let us put some annotations here. This one is the control unit. This one is processing unit 1. This one is processing unit 2. This one is processing unit N. Okay, because the number here, we used N because the number is actually not specified. We cannot specify a certain number, because in some architectures we have 2 CPUs, in some they have 4, in some they have 16, in some supercomputers they may have like 32 or 64 processors or whatever. So that's why we use the N. Okay, or also for data, here they have data 1, data 2, then the data N. Okay, so this one is as I said, memory, or shared memory. Okay, so here the sequence actually of the flow is going to be always from the memory to the control unit. So why? Because the control unit actually is the starting point of any type of execution. So the data actually is going to be called from the control unit, from the memory actually by the control unit. Then that data actually is going to be passed. Sorry. That that instruction, actually this one is I, this one is I. So the instruction, because as we said in the memory we have program and data, right? So the program actually is going to be retrieved from the shared memory by the control unit. Then it will be passed to the processing unit. So in this case, the same instruction actually is going to be passed to multiple processing units. So we still have one single instruction at a time. Even though we have more than one processor. Okay. This instructions actually are going to deal with multiple data. Depends on what this instruction would do. Okay. So that data actually depends on the processor. So the same instruction is given to multiple processors, and every processor could do different or could manipulate different data from the memory. So here in this, based on this instruction or based on this design, actually multiple processors are still doing some parts of the same job. Okay. So maybe the result of the first processing unit could be used by not in here. So the result of the first processing unit actually is going to be saved in the memory, which is not going to be the input of the processing unit number 2, and so on. Okay, so every processor is working independently, even though all of them are running the same instruction. Okay, so there is no kind of shared data between the processors like that. So this one actually is not the case here. Okay, so this one is not the case. Okay. This is, guys, as I said, this is very general information. Actually, this is very general information here for today, because our today's class is very short. That's why I am going to give you a complete hint about this taxonomy to understand what is the meaning of every term, because in the next class, inshallah, next week, we are going to go in deep to understand what is the SISD, what's the SIMD, and so on. And we are going to use all of that terms. That's why I have to explain to you. Okay, so this is the case of the SIMD. Okay, let us delete some lines from here to use the same instruction, the same drawing. Sorry. Okay, what's about the type of this SIMD? Actually, the SIMD, if you can see here, I put some hints here. SIMD is semi-parallel. So we cannot say fully parallel, and we cannot say sequential, because this type actually is, even though they are running the same instruction at the time by multiple processors, every processor still manipulate different data. So we can manipulate multiple data at the same time, even though we still using single instruction. Okay. Somehow it's something between parallel and sequential. Okay. Let us move to the third one, which is MISD. Okay. MISD actually is something similar to this, but even instead of having one control unit, what we will have here is multiple control units. Okay, so the first one is control CU1. Okay, the second is CU2. The third is CUN. Okay, so here instructions always need to be uploaded from the what they call it, memory. So here the memory, or each control unit need to upload its own program, because as we said, for the architecture, this architecture, the program actually is here and the data is here. So also we may have program here, maybe other program, and sorry, the program actually supposed to be shared, something like this. Okay, this is a program, and this is all types of data available in the memory. So from the program here, because as we said, the program has a lot of instructions here. So the control unit number 1 could take the instruction number 1. So here we could use I1. Okay, and here from the same sorry, we cannot use line like that. So from the same program here, we can take the I number 2, and from the same program we can take I number n. So we pass them, or these instructions actually are going to be called by the control unit. Then they have to be pushed to the processing unit like that, in parallel at the same time. So in here we can see now we started dealing with kind of parallelism. Okay, so here we will run multiple instructions at the same time. But here they assume that these processors, all of that processors are still dealing with the same data, like that. So in this case, here we will have a bottleneck actually, because that processors may start waiting for each other, because, for example, the result of the first processing unit is an input for the second processing unit. So also maybe the output of the processing unit 2 is an input for the processing unit number 3, and so on. So for that case, actually, here, event 2, we have multiple control units and multiple processing units that could handle multiple instructions at a certain time. They still cannot run in parallel. They still cannot run in parallel. Why? Because they have to wait for each other. So processing unit 2 may wait for processing unit 1 to finish. Then after that, maybe 3 is waiting for 2, 4 may be waiting for 1 and 5. Maybe n is waiting for them all to finish. So similarly as the example that I explained yesterday in our first class. Okay, so I hope that you still remember that. That case is fully sequential. Okay, so in here actually, even though we have a very expensive architecture which is based on multiple processors, and that multiple processors can run multiple instructions concurrently, they still cannot run in parallel mode. They still cannot run in full parallel mode. So that's why this architecture actually is not practical. So you will never find any computer using this MISD until now, up to my knowledge. Okay, so this architecture actually is a very, very stupid idea, because the what they call it, multi-processing architecture is very expensive, so we cannot build that architecture to run single data at a time, or to manipulate single data at a time. Okay, so that's why this one is not practical. This one also could be commented here as a semi-parallel, or maybe semi-sequential, because it's also something very near to sequential, very close to sequential or full sequential. Okay, the last architecture here we have is the MIMD. Okay, so MIMD here, let me clean this. What we need to do is to clean all of that stuff from here, delete, because the architecture here could be a little bit different. Okay, so now we finished the SISD, we finished also the what they call it here, the SIMD, we finished also the MISD. So now we are going to talk about the MIMD. Okay, what is the MIMD? It is, from its name, is multiple instructions, multiple data. So this is a fully parallel architecture, as you can see here, fully parallel. Okay, from here, based on the memory, so let us draw the memory like that. So this one is shared memory. Okay, shared memory. Oops. Okay, then here inside, what we have like here we have this thing. Let us copy this to keep the same size. Okay, then we have this and that. Okay, let us write some comments here, or we put some notations. So this one is program 1. Here is data 1. Here maybe program 2, data 2. Program N, data N. Okay, so this is what we have in the memory. Also, I did a mistake actually. Okay, this one actually is not a shared memory. Sorry, I confused myself. Okay, let us take this, put it here. Let us remove the shared memory from here. This architecture actually is based on multiple processors and multiple memories. Okay, so this one is program 1, memory 1, program 2, memory 2, program N, memory N. Okay, so here that processing unit actually could run in any of the previous three architectures, and it could be mostly it could be based on SISD or maybe based on SIMD. So here the processing unit actually is based on the first SISD or SIMD. And that we already explained how it can deal with the data which is saved into the memory. That's why I'm not going to explain it back again. But here, what we have to put here actually is what they call it interconnection network. Okay, so this is the interconnection network that's used to communicate or to link or to pass data or to interact between the processing units. So this arrows actually this arrows actually like that, so it can read and write from the memory and the processing unit at the same time. Oops. Drawing using mouse is not a good idea actually. So also this one, sorry, this one actually is something like that. Okay. And also they may have something called shared memory here. Okay, shared memory. Okay, so here this architecture actually is fully parallel. Why fully parallel? Because every processor could run a single instruction at a time. Okay, so here, if let's say we have n processors, so in this that means we can run n instructions at a time with n data that each single data or multi-data could be handled by a certain processor. So this architecture actually is fully parallel, and this is the recent and today's mostly used architecture in every mobile device or in every laptop we see recently. Okay, so that's why our focus actually is going to be on this. So you always keep this in mind. And as I said yesterday in our first class, parallelism actually, or any type of processing, are based on the two main capabilities that completes each other. So the first capability is the processing power, and the second capability is the interconnection network. So if let's say we have very high processing power, but our network is very slow, interconnection network is very slow, then it will become a bottleneck and it will hinder and slow down the processing of our computer or supercomputer. Okay, that's why both of the things, processing power and interconnection network, are very important. To have very high speed processing. Okay, that's all, guys, about today. So if I hope that everything is clear for you, and if you have any question, just take the opportunity and ask me, and I'm ready to help you understand. Okay, guys.
Okay.
I don't know. I don't know why we have 31 in my class. I have only 25 students registered, but suddenly like that we have 31 attendants. Okay. Any question before I finish with this?
No, doctor.
No questions so far, Doctor.
Okay, that's good. Okay, guys. Is there anyone from other groups, maybe, or from outside our class attending our? I have no problem actually with that, but I just want to know. Anyone is not from my class? Oh, no response. Okay, no problem. Okay, guys, thank you for attending. Please don't forget to record your attendance on Butra Blast, which is very important for you guys to enter the final exam, because to enter the final exam, you have to attend at least 85% of the classes. Okay, so please don't forget, and see you inshallah next week. Assalamu alaikum warahmatullah.
Thank you, Doctor.
Thank you, Doctor.
Thank you, Doctor.